We'll begin today by taking a look at a position versus time graph, which I have shown here. Each one of these increments stands for 1 second or 1 meter. So a few things that I'm going to do first is I'm going to walk through second by second what's happening on this graph. And then I'll talk about, you'll notice that all of the lines on this graph are straight lines. Well, what happens if they curve? That's going to come a little bit later. I can tell you right now, in general, if they curve, that means you have acceleration. Later on, I'm going to show you just sketches of graphs where I'm showing you the position versus time, the velocity versus time, and the acceleration versus time, all at the same time. When I do that, what I will end up doing is discussing what happens when the graph curves, and then I'll have a third part where I talk directly about the curves on a graph and what would that tell you about the acceleration and velocity at those points. You will not be responsible for the most part of figuring out what would the velocity be at those points because you want to be able to get the slope of a curve. And so you won't have to worry about the detailed mathematics behind that. So we'll get started with this, and we'll say that the starting position of this is 5 meters. We see on the y-intercept over here, this is 5 at time of 0 seconds. The position is at 5 meters. And from 0 to 3 seconds, the position remains 5 meters. Therefore, we can claim that we are motionless. Now, the next thing that happens is from 3 to 5 seconds, we are moving from 5 meters to 0 meters. So since this has a negative slope, we can say it is a negative velocity. We'll solve what exactly that negative velocity is in a moment. From 5 to 7 seconds, we see that we are once again motionless. The position remains at 0 meters, motionless. Then from 7 to 15 seconds, we are moving from 0 meters to negative 5 meters. Since we're moving in the negative direction, that will again give us a negative velocity. And from 15 to 18 seconds, we are at a position of negative 5 meters. So we are once again motionless. And finally, from 18 to 20 seconds, we are moving from negative 5 meters to negative 3 meters. Therefore, it's a positive velocity. The acceleration is always 0. We know that because there are no curves in the graph. One of the things I want to point out is that the velocity is the slope of the line. So I can go ahead and figure out what the slope of the line is at the 4-second mark, at the 3-second mark, at the 5-second mark. We talked about right here. The 3 to 5 second mark, we have a velocity that is negative. What I see is we have a rise of negative 5 and a run of 2. So for the 3 to 5 second mark, I can go ahead and claim that it's negative 5 meters per 2 seconds. Therefore, the velocity is negative 2.5 meters per second. Looking at this segment here, this is negative 5 meters. That spans 8 seconds. So from 7 to 15 seconds, we have negative 5 meters per 8 seconds. That will be a negative 0.625 meters per second for a velocity. Notice that this line here from 3 to 5 seconds is much more steep than this line here from 7 to 15 seconds. So an additional note that I can put is not only is the velocity and the slope of the line, but the steeper the line, the greater the magnitude of the velocity. Obviously, negative 0.625 is a bigger number than negative 2.5, but again, in physics, the negative just indicates a direction. It does not indicate a size. the negative 2.5 meters per second is still faster than the negative 0.625. This last phase here from 18 to 20 seconds, it's a gain of 2 meters over 2 seconds. So from 18 to 20 seconds, we can say that we gained 2 meters in 2 seconds, so we had a velocity of 1 meter per second. The fastest motion in this graph occurred from 3 to 5 seconds. The slowest motion was when we were motionless, from 0 to 3, from 5 to 7, and from 15 to 18. Other questions you'll typically get asked is, what was the distance traveled? So if we look at the distance traveled, for the first 3 seconds, we traveled 0 meters. Then the next 2 seconds, we traveled 5 meters. And then we traveled 0 meters. And then another 5 meters. Then 0 meters. And then finally 2 meters. So my distance traveled, distance would be 0 plus 5 plus 0 plus 5 plus 0 plus 2, or 12 meters. Once I have a distance, I can get the average speed. So the average speed is done over a period of time. The average speed would be 12 meters in 20 seconds, or 0.60 meters per second. Displacement's a little bit easier to figure out than distance, because displacement only cares about your initial and your final. I'll create some room here so I can write. The final position right here is negative 3, so I'll put x equals negative 3. The initial position right here is at 5, so x initial is 5. So delta x would be final minus initial, so that will be negative 3 minus 5, or negative 8 meters. So the displacement is negative 8 meters. The average velocity, so this is not an instantaneous like we calculated here, here, and here. This is an average velocity. The average velocity would be, so average v would be negative 8 over 20, negative 8 meters over 20 seconds, or negative 0.40 meters per second. Quick clarification on these instantaneous velocities. Let's say you're asked, what's the velocity at 10 seconds? So we go to the 10-second mark, which we see right here. At the 10-second mark, I just need to know what the slope of the line is at this point. Well, the slope of the line from 7 to 15 seconds is continuously negative 0.625. So the velocity here, and right here at 10 seconds, and all along this line, the instantaneous velocity is negative 0.625 meters per second. Next thing we'll take a look at is some sketches of graphs, and in there, not immediately, but eventually we'll introduce curves. But what I want to talk about is, well, what does a velocity versus time graph look like that corresponds to this? A kind of quick preview is, since the velocity versus time is dependent on the slopes of this graph, for the first 3 seconds, the velocity versus time graph should be directly sitting at the x-axis. Then I see from 3 to 5 seconds, I have a negative velocity. So it is a continuous negative 2.5, so I would have a horizontal line. Then from 5 to 7 seconds, I would go back to being directly on the x-axis. From 7 to 15 seconds, I would be negative again, but not as negative as I was before. And the process continues on and on and on throughout this. You'll see some more in the sketches that are coming up. Next thing we'll look at is how one graph impacts another. So starting with position versus time graphs, let's say, for example, you have a position versus time graph that looks like this, which shows a constant position being maintained. That means your velocity versus time graph and your acceleration versus time graph would both be no slope at 0. Do something a little bit more interesting. Perhaps the position versus time graph looks like this. In this case, we have a constant positive velocity, so that will be a horizontal line on the velocity, and no acceleration. It doesn't matter whether the position versus time graph had the line in blue, or the line in red, or perhaps this line in green. As long as that slope is the same, if all three of these lines have the same slope, the red line on the velocity versus time graph satisfies everything that you need to continue onwards to the PvT and the AVT graphs. Similarly, if the position versus time was like so, or like so shown in blue, or that shown in, that's shown in green, the only thing that really matters for the velocity versus time graph is the slope of those lines. So all three of those would produce this same line on the velocity versus time graph, and then the same line on the acceleration versus time. In that particular case, we're talking about a situation in which you have a constant velocity that is negative and you have no acceleration. Now let's get a little bit more complicated. Let's say the position versus time graph looks like a parabola, as shown. The velocity versus time graph would start positive because we have positive slope here. It would hit 0 and then it would become negative. So the velocity versus time graph might look something like this, a straight line. Notice that this is quadratic in nature. So what I mean by quadratic in nature is that in some way, shape, or form, x is related to t squared, a parabola. So here, v will be related to t, a line. And then the acceleration is going to conclude by being a horizontal line with no slope. This would be negative because it must match the negative slope in the PvT graph. The way position, velocity, and acceleration relate to each other is based on powers. If this is a power of 2, as seen in t squared, this is a power of 1 as t to the first. This is a power of 0 as t to the 0. We can get a little bit more complex if we wanted to. We could take a look at, would it make a difference if the parabola was upside down? And obviously, yes, it will. It will change the velocity versus time graph to be sloped like so. The acceleration would then be a positive acceleration. For the most part, these are pretty much the only shapes that you're going to really see in the graphs. We'll go through just a few more quick examples. We want to get a little bit more complex. Perhaps we have it curving one way, such as a parabola that is shaped as an upside down U, shown here. That turns into a right side up U, shown here. That would cause our velocity. Notice that this whole time the slope is negative. It becomes very negative here, but then it still maintains being negative and comes back to 0. So we would be looking at a velocity graph that looks like a V that's upside down like so. Now the acceleration graph would be a horizontal line that abruptly changes to a horizontal line that is positive. We can take a look at what we call the concavity of a graph to emphasize what's happening with the acceleration. If your position versus time graph is shaped like this is called a negative concavity and will result in negative acceleration. If it is shaped like this is positive concavity or positive acceleration. You can take a circle to demonstrate what's happening with the position versus time graph. So I'll take a circle and I will split this into quarters. And I want you to imagine that the circle itself are curves shown on the position versus time graph. So we have what we have here is one curve shown in quadrant 1, a second curve in quadrant 2, a third curve in quadrant 3, and a fourth curve in quadrant 4. Now each one of these quadrants will tell us a certain particular behavior about velocity and acceleration. What I can tell you is if you are at one of the upper curves, that means you're concave down and that gives you a negative acceleration. If you're one of the bottom curves, that means you're concave up and that's a positive acceleration. In The next thing is how the slopes work. So in quadrants 2 and 4, as you move from left to right, you are gaining y value, therefore you have a positive slope. So this would be a positive velocity, this would be a positive velocity. In quadrants 1 and 3, as you move from left to right, you are losing y value, so that's a negative slope, therefore negative velocity, negative velocity. Anytime you're in quadrants 1 or 2, you are going to have a negative acceleration. Anytime you're in quadrants 3 and 4, you would have a positive acceleration. So what I do when I think about the graphs, coming back to this one here, I just look at the curve that I'm given for the position versus time, and just from matching which quadrant 1, 2, 3, or 4 would it be in, I can talk about whether the acceleration is positive, negative. Same thing with the velocity, is it positive or negative? So for example, if I have a curve like this is matching a curve from the circle in quadrant 4. So I'm going to have a positive acceleration and a positive velocity.